So what we are going to cover here about phase analysis, that I know a lot. Then present the hypothesis and goals, the methods which make good image vision, how in the image in the microscope, image stitching and filtering. Then I'm going to pass through the results and finally the conclusions and what we are going to do next in the next step of this project. So what motivates us to do the most key? There are different kinds of them. We are going to focus and work with two. The nevus, which is our control, is defined as benign melanocyte proliferation on your skin. And on the other hand, you have the melanoma, which is a malignant tumor that can arise mainly on the skin, but also on eyes and nervous systems. Here in Uruguay, it's the second most increasing cancer disease after lung, and it has a high lethality in advanced stages. So the doctor does the diagnostic. The first things they do is they look at they look into your skin and they use the ABC rule, which is an acronym for asymmetric, border, color, and diameters. They look if it is asymmetric. They found irregular borders, like in the second image here. They see if there are the diameter millimeters, and then they see if it's changed throughout time. This here, I just want to show you, is a dermatoscopy, which use polarized light, so the dermatologists can see deeper into your skin. And then the skin pathology, it's surgical. They remove you the sample, and the anatomopathology or the dermopathologist is specialized on to thickness, presence of ulceration. It's like well, there's patterns on that. So then a kind of techniques that there have been using nowadays is multiphoton microscopy. And in multiphoton microscopy, you can penetrate deep into the tissue, a couple of hundred micrometers. You reach all the stratified layers. And in some research, concentration of FAD bound to protein increase in melanomas. However, this is a little expensive and hard to access technology. So you have already talked about phasor in hyperspectral imaging. You essentially have a stack of images varying in lambda. Then you get the intensity spectrum here, and the phasor analysis, the phasor transform actually relies on Fourier phase transform, which is essentially two equations. I mean, if you are in a complex space, you split apart the transform and you get the coordinates to plot it. Then you relate it, you assign a color in the pseudocolor image. This process in an image is something. What I want to tell you here, I mean, what I want to highlight here is that what you essentially, users essentially don't know or don't is S and G images. You acquire your image and then to the phasor. But here, I'm going to work here because we are going to process this kind of data. So what are our hypotheses? Well, there are metabolic fingerprints in nevus and melanomas that allow us of them in hyperspectral image, using hyperspectral imaging in non-stained samples. I mean, they're not going to use any label, just autofluorescence. So our goals were to evaluate the potential of to differentiate decision protocol and then to image algorithms to do this. So we work with two kinds of to compare. Now, can you hear me? Perfect. And then the non-stain paraffin, which I use in the microscope. Here is the setup that we use. We acquire 100 images from 50 patients. We take an excitation laser for 5 nanometers, and we get a lot of tile image ranging from different sizes. And that's now because this image, perfect. This image, it's extremely big. It's a tissue. It's this one here, but actually it's not as big as this one. And acquiring this image take about 5 hours. It's 3 billion pixels to the way. These arise some problems because we have to reveal the image, you have to overlap the tiles, and you have to know what happens in the overlapping regions because you have repeated information, okay? And the other problem is computational one, how we process this kind of data. And it's not only one, right? There are a couple of hundred images. So to do that, how we choose region. I mentioned before X and Y images. These are the coordinates of the phasors, and the first here is that mismatch, or you can average or take one of the borders, and if you do it wrong, you are going to end up misclassifying the components, okay? Because if a pixel here corresponds to the coordinate, if it is mismatch, it's going to be in another component. So to overcome that, we developed some algorithms. This is the first image you acquire, which is the repeated information, the redundant information. This is the first approach we did that you can see it has some like ghost effect on the image here. Can you see the point? The pointer? Okay. And this is the optimized algorithms, which you don't see this kind of effect. So the other dimension was about how we compute this huge amount of data. The first thing we do is to stitch the image, reveal the entire image, compute the phasor, but this may probably create an overflow in the computer. You won't be able to do it. The computer just stops. So we propose, and that's the important thing of this, to compute the phasor in every tile first. Acquire, you won't have overflow here. Acquire G image and S image, but for every tile, and then to stitch again. Okay. So the last part of the methods were to, I mentioned before, I spent 5 hours acquiring image, okay? If we would like to reduce the noise on the image, we can acquire it in the microscope with many times on the same image. The problem here is that the if you want to take a couple of days maybe. So we propose to apply image filterings in order to get a similar result here. And what we get applying filters into the phasor is this image. This is the same, here's the pointer, the same image than this, but we filter the phasor, we filter the G and S images. So we could reduce the scattering and disperse on the phasor. It's also the acquisition time reduces, of course. It can decrease the position time to the laser, so you damage less the sample. So far, so good. Well, what we get here, develop an acquisition within to compute the phase, and finally we have image. What are the results? This is the hematocylin eosin image from the nebulous, the hyperspectral image, the phasor that you can see here. It's the major components are between 90 degrees, and the pseudocolor image we get in this scale that we did it. It's about it's everything green because it corresponds to the range from 19 to 100. And well, what's happened with the melanoma now? Look at this. This is the segmentic injure where the lesion is, the same data, the phasor, which you can see it has bigger faces here, and also something here, which is, well, another component. And how do you see the pseudocolor image? The lesion that the pathology segmented has a very different face on the phasor that you can see it in blue and sky blue and violet. So we asked what is going on here or what we can see there. You know, it's fixed samples, so there are no metabolism, but we obtained and NADH phasors in order to overlap them. So what we can see is that the main component in the nebulous is present near the NADH, while in the melanoma you can see mainly three components, NADH, FID, and something else here, which may probably be the melanin. How we know that? Well, we get deeper into the tissue. We see melanocytes, a nest of melanocytes, which are a cluster of melanocytes. And in these structures here, I don't know if you can appreciate it, but this is a nest of melanocytes. This is the phasor of this image, and all of them are more green. However, when you see the nested here of melanomas, they all have two main components that are closer to FID. So we conclude that our acquisition protocol and image processing pipeline reduces the time and let us obtain a differentiate in both cases, melanomas and nebulous. The image filtering reduces the acquisition time, decreases the sample damage, and this method can optimize and increase certainty when the pathologist uses to make their diagnosis. So what's next? Well, we have actually three parts here. We are using ML, machine learning in this kind of problem. Sophia, which is the dermatologist working with me, she's going to use the 2-photon microscope here in the hospital to study metabolism. And then I told you about some algorithms and some pipelines we developed to process this kind of data. So I'm going to focus on this now, the software development, Python and NumPy. So for any of you that doesn't know, Python is a programming language. It's a general purpose language. You can do almost like web development, output stuff, data analysis, data processing. And it's essentially structured in libraries, like a library, which is a set of algorithms, okay? These are some of them, like NumPy, SciPy, that you have a set of algorithms, you use it, you program. So why don't you have our own, okay? The first of Py. So we started, all the algorithms we use it, we publish them as a library, a little one because it has few functions yet. We get funded by CCI to develop this for 2 years. This is the publication in the official page. Actually, you can install and try it. And then there is a little thing. Many of you doesn't program, right? So you're going to tell me that that's great, but I can use the Python. So what's the solution for that? It's Napari, which is an interactive image. It's essentially you download and you click things to do the process, right? Like image A, PG. So we also get founded to do this. This is for an year, so in a couple of months, I hope to have the first version. You can try it. And this the plugin is going to work. And this is an example of plugin. And this plugin is going to work in hyperspectral imaging. I mean, because the PI library covers much more like film and another features, but this is going to feature hyperspectral imaging, and that's it. I would